Hello everyone, in this video series I'll be reviewing the paper Cognitive Architectures for Language Agents. I think that this paper is quite insightful and will be important in years to come. In the first part of the series, we will be looking at the motivation behind CoALA. What are the trends in AI that led to this work? First, we need to introduce this term in the title, cognitive architecture, because it's not something you see commonly used these days. So cognitive architecture has two aspects to it. So the first is the theory of the structure of the human mind. What are the building blocks that generate cognition? The other aspect to it is the computational instantiation. How can we write software to emulate these processes? For example, cognitive architectures explicitly implement perception, memory, and planning. And by now you might be thinking, wait, isn't this the whole agents revolution that we have been hearing about these days? We'll get back to that. So to understand what a cognitive architecture looks like and what it can do, let's do a quick walkthrough of the SAW cognitive architecture in the image here. SAW has various memories to track the agent's state. It has a short-term working memory to track the agent's current circumstances, like its results from reasoning, its perceptual input, and its goals. SAW also has three types of long-term memories, namely one for holding the skills of the agent, known as the procedural memory, one for holding facts about the world, also known as semantic memory, and one for sequences of its past behavior, also known as episodic memory. Why is there a need to categorize the different types of memories? Well, here's some food for thought. In humans, procedural memory tends to be stickier than episodic memory. Once you learn how to ride a bicycle, you retain the skill even if it's not practiced for months or even years. Contrast this with the memory of what you ate for lunch 3 days ago. Different memories have different properties. This is how SAW makes a decision. In SAW, its action is known as an operator. It can modify internal variables or interact with the external environment. Now, which of these operators should the agent use in the end? This is where rules come in. Here's an example. Say we have a robot who wants to pick up an object. We have a rule that will check for these conditions. If the goal is to pick up an object, and the robot can see the object, the robot is lined up with the object and not close enough to the object, then we propose the move forward operator. This whole unit here is also called an operator proposal rule. Now, multiple operators will be proposed, so there will also be rules for evaluation and selection of the right operator to apply. And then the cycle repeats. SAW is also capable of storing new facts and experiences into its long-term memory. When it initially gets stuck on a task and then manages to resolve it, new rules are created and learned through this process called chunking, effectively updating its source code. It also uses reinforcement learning to tune the selection of operators. What I find interesting that's not mentioned in the paper is SAW's ability to use reinforcement learning to learn retrievals from episodic memory. The n-gram viewer in the image, which shows the share of cognitive architecture mentions in Google Books, pretty much sums up his history. It seems like cognitive architectures have identified a lot of the problems to tackle when building intelligent agents, and they have provided some answers. Its golden era was a few decades ago, with SAW starting around 1983. Hundreds of architectures were proposed, but somehow, over the past decade or so, interest has waned. Why? Remember that back then, symbolic AI was the dominant paradigm of AI research. Cognitive architectures were limited to domains that can be specified by logical predicates. Also, they require many pre-specified rules to function. An example would be the image on the right from the SAW tutorial on solving a problem where given jugs of different volumes and the option to fill any jug or pour water from one jug to another, find a way to arrive at a specific volume in a specific jug. Look at the amount of things to specify in just this one rule out of many rules required. This resulted in rigid systems which have poor generalizability and is labor intensive to construct. It is no surprise that its popularity declined over the years. Now, let's move on to a more familiar trend in recent years, language agents. To recap, in Figure A, LLMs were initially used as a simple input-output black box. However, LLMs alone have limited knowledge and reasoning. Its knowledge does not update after pre-training, and this bottlenecks the amount of reasoning it can perform. Soon, researchers figured out that instead of having to label task-specific knowledge to train their model, they can obtain task-specific info from LLMs, as the latter have strong common sense priors and semantic knowledge of the world. This leads to early language agents in Figure B, where LLMs are interfaced to external environments to perform tasks. For example, consider a robot environment where to complete a task, it needs to know which actions to take. A robot has many potential actions, so how do we get it to recognize which action is the right one? In SayCan, LLMs are used to upweight actions based on their text label, if they are valid next steps in achieving the task. However, these language agents still suffer from the same problem of frozen knowledge. To mitigate this, agents are then equipped with memory and reasoning, as in Figure C. With reasoning, lessons can be concluded from environment interactions. With memory, these lessons can be stored and retrieved for future use. In parallel, memories can be in the form of existing human knowledge in a database. Agents can also have multi-step reasoning processes before it chooses the next action. Now that we have introduced the two key ideas, cognitive architectures and language agents, let's recap. Why are we reviving an old idea? What is different this time? In cognitive architectures, we need to specify the domain properly. On the other hand, LLMs can take in arbitrary text, which eliminates the need for such specification assuming the knowledge is acquired during pre-training. Which brings us to the next point. Cognitive architectures, after specifying the domain, require specification of initial rules and operators, which are basically the AI skills, so that it can build on top of these skills to learn new things. On the other hand, LLMs acquire a lot of these skills and knowledge from pre-training that they can solve some tasks right from the beginning. They also know some things about the world and have some common sense. Most importantly, there's a new capability that didn't exist previously, flexible reasoning at the push of a button. For example, you can ask an LLM, simplify this paragraph for me, or who are the people mentioned in this text, when previously you might need to train a model for each specific task. However, this knowledge is frozen after training, and LLMs do not have a memory for events and the flow of time. In cognitive architectures, memory, learning, and retrieval are designed right from the beginning, and its interactions have been thought through over the years. LLMs are less interpretable as they are characterized by their weights, which are a bunch of numbers. As such, it can be hard to catch when they hallucinate. Meanwhile, cognitive architectures largely makes use of interpretable symbols and integrates grounding techniques to connect these symbols, such as words, to the real-world objects or concepts that they refer to. At last, after reviewing both historical and recent developments in AI, we can finally answer, what is CoALA? CoALA was written by a group from Princeton NLP, and you might recognize that some of the authors were also co-authors on React, Reflection, and Tree of Thoughts. CoALA is a conceptual framework for language agents with memory components, structured action spaces, and decision processes to choose actions. They aim to learn from the past to guide the design of modern agents. They start off by organizing recent agent research by mapping their components onto the CoALA framework. From there, they identify gaps in current research and propose actionable directions. To better appreciate how important historical developments were, let's compare CoALA and SAW side by side. We'll go into CoALA later, but look at the similarities and how much was really thought through in the past.